Okay, welcome. This is the week 10 webinar. We're getting close. We only have one left after today's. And this webinar is going to be all about regression analysis. That's kind of the point. So as always, I'll answer any questions you might have. Always happy to answer questions. And then after that, we're going to talk about scatter plots. It was kind of briefly mentioned in chapter 2, but now we're going to get into more detail a little bit and kind of see how those work. We're also going to look at, I know this looks easier, it's just a letter R, but it's a lot deeper than it looks. And that is the correlation. So we're going to be talking about the correlation between two things. And then we'll look at R squared, which is more than just the square of R. It has meaning, and it talks about how helpful something is to predict something else. And then we'll talk about the equation of the regression line. So today is a day where you definitely got to remember what lines are. Slope and y-intercept are going to be important. And we'll talk about how to interpret those in terms of dealing with looking at regression analysis when we've got a couple variables. I'm going to doubly remind you to avoid causation. It's kind of the number one mistake that's lots of people make in regression analysis is they use words and they talk about how this causes another thing, which isn't what you can talk about. And I'll give you some advice on that, on how to avoid causation. Then, because this is statistics, and as I mentioned, almost the whole last half of the class, we do hypothesis testing. We're going to do a hypothesis test for rho. Rho is the correlation. It's actually the Greek letter for R. And the question is there a correlation or isn't there? And that'll be what the hypothesis test is all about. So that is the plan. I'd always like to remind you in terms of the schedule coming up. Again, we're in week 10. So, we're counting the days in a way. Monday, 6 days from today, will be the last webinar. So I don't do a webinar in week 12 because the class is just pretty much over, almost over. There's no new material to talk about in week 12. So next week will be our last webinar, and that will be on Monday evening. And then a week from Sunday is the absolute deadline for your project. So hopefully you're all making some progress on your project. I'm not seeing a lot of comments in the project 2 discussion board about what your project ideas are. And the hope was by now you're all supposed to let me know so that I can help you and guide you through the process. So the hope is as soon as you can, you and your partners or partner, get together, decide what your null hypothesis, what your alternative hypothesis will be for the project, and how you're going to get your data, and who your client is, and kind of post that on the project 2 discussion board. And then I'll let you know if it can work or not. Again, don't wait until the last minute. The hope is in a week or so, you've got a rough draft for me. I do want to let you know a week from today and a week from tomorrow, I'm going to be pretty much offline. So that Tuesday and Wednesday of next week, I'll not be available because I'm going to be backpacking. And I won't have any internet connection or any ability to communicate with anybody. So just let you know that is a week from today and a week from tomorrow. So that's the 18th and 19th of June is I'll be pretty much completely offline. So you want to, ask me project questions before then so that I can answer them. So hopefully that makes some sense. And again, we all have lives, and I do have it. We have that June 19th completely off, and I actually don't teach on Tuesdays, so I'm taking those 2 days for backpacking. So are there any questions about anything? And I'll be checking the chat box throughout. Any questions? Any questions? Okay, I have a question for you then. And here is the question. And you need to answer because we need some data and there aren't that many of you here, so I need to make sure we have an answer. That is including yourself. How many siblings do you have in your family? And put that in the chat box. Should be real quick to type the number in. So everyone put it in. I'll even put it in too. My guess is you would never guess how many I have in my family. It can't be 0 because you're alive. Could be 1, but it can't be 0. Does that make sense? Yeah, because you're including yourself. I'll put mine in. There's mine, 4.5. And that is a half sibling. And then how many minutes do you spend exercising in a typical 7 days? How many minutes typically? And again, just kind of make a good broad guess. Do you spend exercising in a typical 7 days? And I'll put mine in. I tend to be an outlier. Yeah, I'm an outlier. I exercise a lot. I had a beautiful hike today, hours and hours, and it was wonderful. Started at 7:30 in the morning. Okay, so what we're gonna do is I am going to pop the answers, and I'm gonna write them as 2 comma, sorry if I have to scroll down a bit, 220. And then we have 3 comma 180. And then we have 1 comma 240. And then we had 4.5 comma 720. And that's all our data. You know, sometimes you can only get so much data. It's always better to get more, but it's all we can get. Okay, so what we have is we have a collection of data. And what we want to do is we want to say, well, is there a relationship between number of siblings a person has and how many minutes they spend exercising in a typical 7 days? Okay. And what we're interested in, it turns out, is are they correlated? And if we know 1, based on the regression line, and how can we predict what the other is? So if you have an idea of how many siblings someone has, is that going to help you predict the amount someone exercises? Or maybe it won't help you predict. Any questions on the idea? All right, so that's kind of what we're going to be looking at. I want to show you the calculator. I'm not going to do everything with the calculator, but we can get the idea. So you might be able to guess. Here's a hint. We're very close to the end of the class. What calculator and number do you think I want to use? Yeah, calculator 24. We're almost at the end. And again, I made this calculator in basically the order at which we do things. And this is our second to last week of the class. You can guess what's going to happen next week. So I go to regression analysis. And there's a few ways of doing it. I think I'm going to do it this way because it's a little faster. I'm going to put in the values of x. And the values of x are 2, 3, 1, and 4.5. And then I'm going to put in the values of y, which will be 220, 180. and then 240, 720. And then we hit plot points. And what this shows me is it shows me a scatter plot. So do you remember the word scatter plot? Basically, all it does is it takes the data where you have an X and a Y coordinate for every person, and it plots them. So you can see that it plotted all the points. You kind of see. Okay, and again, we have a small, because we only have so many people here, but we have a very small, sample size. So we're not going to get too much great information, but we got a little bit. Then you can see that here are the points. Here's a scatter plot. And then what it does is it draws a line that is what they call the best fitting line, which is called the regression line or the linear regression line, which is the line that kind of fits the points the best, which pretty much what that says is look at the Y value at the line for that point and look at the Y value of the point. See how far away they are from each other for each of these. Square those distances, and of all possible lines, this particular line that we see will give you that minimal sum of squared differences. And that's what the regression line does. Any questions on this? Any questions? Kind of see the picture. And we can see as sibling goes up, we can see there's a tendency for the amount of exercise to also go up. Doesn't mean that it always goes up, because notice that like from here to here, it went down. But kind of the best fitting line shows it goes up. Any questions so far? Okay, so the correlation, we use the letter R for correlation. And I guess maybe I don't know, but maybe it has to do with there's two R's in the word correlation, but I really don't know. So it's a correlation. The correlation is always a number between -1 and 1. Okay, so if you ever think R is 10, you're wrong. Okay, R can never be smaller than -1, and it can never be bigger than 1. It can be negative. It can be like -0.2 or whatever, but it can't be that far away from 0. Okay, R has the same sign as the sign of the slope. So you'll see our slope is positive because it goes upwards as we read from left to right. And that means we have a positive slope, which means R will be positive. Okay, if R is close to -1, the points are close to all being on a negatively sloped line. If R is close to 1, the points are all close to being on a positively sloped line. If R is close to 0, then there's no line that fits the points well. Okay. And I like to think, although if you live in LA, you may not be able to see it, but in Tahoe, it's great. We look up at the sky at night and we see all the stars. And they're all over the place. There isn't some line that connects the stars in any nice way whatsoever. Okay. So R will be very close to 0 when you're looking at the stars. It won't be exactly 0, but it'll be very, very close to 0 because they're not even close to being linear. Any questions on that idea? Okay. So the R we got, by the way, was about 0.78, which is actually pretty high. It was a correlation. Not perfect, but it's closer to 1 than it is to 0. So then let's see, can you think of a real life example of 2 survey questions or measurements where R is 1? Let's see if you can say it or post in the chat box an example where you're going to have a correlation of exactly 1. See if you can come up with one. Give you a minute or so to think about one and put it in the chat box. So when would the correlation be exactly 1? And there's lots of examples. Could you do the correlation of probability? Actually, I have no idea what you're asking. I'm not sure what correlation of probability means. Because correlation is a number that tells you how good a linear fit it is for a bunch of data points. I'm not sure you mean correlation of probability. So if you're confused about the question, it's too confusing question to ask. Yeah, because we will talk about a little about probability in this class today, but not really a correlation thing so much. Any ideas of something that has exactly 1 for the correlation? I don't see y'all jumping into the chat box. Not, let me give you one. Okay, let's suppose the survey questions were how tall are you in inches and how tall are you in centimeters? Well, if somebody is, a certain height in inches, you know exactly how tall they are in centimeters because there's a math equation that's linear. Does that make sense? So that would be an example where you'd have a correlation of exactly 1 because you have a linear fit. Every point is exactly on a line. Any questions on that? Because you know exactly how many centimeters they are if they tell you how many inches they are. I mean, when I say it means you can find out online. Okay, any questions on that idea? All right, can you think of a real life example of 2 survey questions where R is very close to 0? I gave you the one with the night sky. That would be like, how many degrees north and how many degrees west is a star. But there's others. See if you can come up with an example where you're going to get R very close to 0. There's lots of examples. Any ideas? You can pop in the chat box. So think of an example where R will be very close to 0. All right, I don't see y'all jumping in. It's always good to try and think of some. All right, let me give you another one. So let's suppose we have the question, what's the temperature right now in Salt Lake Tahoe? Okay. And the second question is, what was the total number of points in the soccer game at the main high school in New Zealand, at the biggest high school in New Zealand? Do you think they have anything to do with each other? The temperature in South Lake Tahoe, California, and the number of points that soccer players are scoring in New Zealand? Yeah, they have nothing to do with each other. You're not going to have any correlation whatsoever between those 2 things. I can't even imagine there being a correlation because they have nothing to do with each other. Does that make sense? So if 2 things don't really have anything to do with each other, you're going to get a 0 correlation or real close to 0. Okay, how about this one? Let's see if you can come up with an example where the correlation is close to -1. Not perfectly -1, but close to -1. See if you can come up with an idea. So it'd be 2 survey questions or 2 pieces of data you're collecting, 2 data values. See how jumping in. Maybe I'll give you my example. So let's suppose the first question was, how many cigarettes do you smoke every day? And the second, after asking that question, how long are they going to live? Okay, so we're going to look at how many cigarettes people smoke and how long they live. Okay, so just a note, I hope you all know this, but smoking cigarettes is not good for your health. Do you all know that? If not, then I don't know where you're from. Smoking cigarettes is very bad for your health. And there is a very strong correlation between amount of cigarettes people smoke a day and how long they live. But that correlation is a negative correlation, because if you smoke a lot, you tend to have a shorter life. Does that make sense? Any questions on that? Okay, does that mean that if you don't smoke, you will live longer? Yeah, it doesn't mean that. You can never use the word will. Will is a very dangerous word for regression analysis, by the way. Okay. But what you can do is you can say that if someone smokes a lot, you can predict that they will not live as long. Do you see? Predict is different than will. Any questions on the cigarette example? Okay, and there's lots of examples that have a, positive correlation or negative correlation or close to 0. Lots and lots of examples. All right, so then comes R squared. So R squared, so one thing, mathematically, it's actually very easy. If you know R, you just multiply R times R, that's R squared, and that'll give you a new number. Okay, but it turns out that it has its own very important meaning, okay, and usage. And that is, first thing, it's easier to talk about R squared if you turn it into a percent from its decimal. And what it means is the variation, and you can think of that as a standard deviation, in the y variable is considered large. But if you just look at y values that all have x values that are almost the same, then on average, the variation, which is the standard deviation, is reduced by that R squared percent. I'll let you read through this, make sure you understand it, because it's a little hard, and we'll look at our example. So in particular, our example had R squared about 0.61. If you round to 2 decimal places, I'm rounding to 2 decimal places because I want to turn to a percent, and 0.61 is 61%. So R squared is 61%. So what we can say is the variation, let me make this a little bigger. So the variation in the number of minutes per week people exercise is quite large. But if we just look at cohorts of people who all have the same number of siblings, then on average, the variation of exercise minutes per week goes down by 61%. Any questions on that? Another way of saying this sometimes that people do, let me write this out, is 61% of the variation of exercise minutes per week can be explained by the number of siblings that people have in their families. And 39% is due to other factors. How did I get the 39%, by the way? Hint is it wasn't that hard. Not no siblings. Any other thoughts? So 61% can be explained by number of siblings. So if you take 100% minus 61%, that's how much you have left. 100 minus 61 is 39. So that's how I got that 39, because the 39% is 1 minus r squared as a percent. Any questions on that? Anyone lost? Okay. So in this case, it says that it's pretty important to know how many siblings someone has to predict how much they're going to exercise. Does that say that if somebody has more siblings, then they're going to exercise more? What do you think? Does that say that if someone has more siblings, they'll exercise more? So for example, if let's say you're 16 years old and your parents decide to have another kid, they have the baby. Are you going to start exercising more because of the baby? What do you think? Given that we know that we had a 61% r squared. Don't see y'all jumping in. It's always a good idea to, answer, at least take a guess. I don't say your name on YouTube, by the way. Okay. Yeah, it's no, you can't say that because correlation can never be used to talk about cause and effect. So having another sibling does not necessarily make you exercise more. It might be something else that makes both happen. You see how that works? Okay, it might be some cultural thing. Could be that there's having a lot of siblings and exercising a lot fits in some cultures. Having not so many siblings and not exercise much fits in other cultures. It may be cultural. Doesn't mean it's causative. You see how that works? There could be lots of reasons. Okay. So here's another example I have. We have lots of examples because examples are important. So let's look at city population size in thousands versus crime rate per thousand. And I looked this up and R was equal to negative 0.36. Okay. So we can say negative 0.36 is pretty close to 0. So there's a weak negative correlation between city size and crime rate. Okay, if you square 0.36, you get 0.13 or 13%. So we can say there's a large variation in crime rate from city to city. But if we only look at cities that have all similar population sizes, then the variation in crime rate is reduced on average by 13%. Any questions on this interpretation of R squared? I'm doing a lot of examples because that's often the most difficult piece of regression analysis is understanding R squared. It's a lot of writing. Any questions? Oh yeah, and I should remind you, this is week 10. And what's important about the number 10? Yeah. It's an even number, so it's an exam week. So I should give you the reminder that this week by Sunday, then and I recommend by Saturday or Friday, have your exam done so that you're done. Because waiting till the very last minute, your network could go down and then you're screwed. So it is important to not wait till the last minute because things can go wrong. So it is week 10. You will be having an exam. And by the way, just like all exams, the last few questions are going to be written. You have to type it out. And I grade those by hand. And you're going to be asked stuff about regression analysis, kind of all the things I'm going over today. And you have to kind of use the language that I'm using. You don't use the language I'm using, then I take off points, by the way. So that is important. All right, so let me talk about the most important statistics that's ever been done in Lake Tahoe. Okay. And any of you, I don't think any of you are from or live in Lake Tahoe, but who's been to Lake Tahoe? Never been? How about the others? Have you been to Lake Tahoe? Aha, you've been many times? So you probably know how beautiful our lake is, right? Yeah, I strongly recommend visiting Lake Tahoe because it is one of the prettiest places of all America. Okay, and not just because I live here, by the way. It's the other way. It's not beautiful because I live here. I live here because it's beautiful. That brought me here. Okay, it's hard to say no once I saw Lake Tahoe. So just to note, and one of the most important things, maybe the most important thing for Lake Tahoe is to keep it beautiful. And in the lake itself is just crystal clear and blue. And if you drop something, you can see it way deep because it's so clear. And we definitely want to keep our lake clear instead of mushy and ugly. So it turns out, this is one of my favorite stories in all of mathematics that I've had, is one of my statistics students. This was a very long time ago, around 25 or so, maybe 24 years ago. My student was able to see the President of the United States. He came to Tahoe to look at the issues we were having with lake clarity and to see what we could do about stopping pollution. Okay. Anyone know who the president was 25 years ago? History. This isn't math. Let's see, jumping in. President Clinton. Not one Bush, it was Clinton. So it's funny that, yeah. So it wasn't Bush, it was Clinton. And Clinton was there. And one thing that I really like about Clinton is he understands statistics. Isn't that cool? I think it's important to have a president who understands statistics. So instead of just like, hear rumors, they can actually look at data and, understand it and make decisions based on, data. So what they were able to show them, and this, by the way, was done by UC Davis. And UC Davis is in charge of the environmental research in Lake Tahoe. And what they did is each year they would measure the clarity of the lake. And what they would do is they would take what's called a Secchi dish, which is basically a plate, like a white plate, and tie it to a string and let it fall down until they kept going and going and going until they couldn't see it anymore. And then they marked how deep that depth of clarity was. And they did that every year for many years. And I talked to the UC Davis team and I asked them, well, how'd you collect your data? And did you just look at one day for the whole year? Because that actually has some issues with regression analysis. And what the researcher told me just made me smile so much. He said, no, they collected multiple days. I asked him how many days. Any guess what he told me to make me smile? He jumping in? 31 days. Why do you think they measured at 31 days? 31 different days in the year. Turns out there had to be a little cloud cover, or if there's no cloud cover, then there's a reflection you can't really see down. But they made sure that there's a little cloud cover for 31 days with no precipitation happening. Okay. So remember in your project, if you don't have a sample size greater than 30, so 31 is a minimum, then you really can't do statistics. Okay, so in the real world, you need it. And this was like one of the coolest real world examples I've ever seen. And that's what they did. So they knew that since they were taking an average of 31 days, then they can use essential limit theorem and say you have an approximate normal distribution and everything works really well. And then what they can do is they can use really solid regression analysis. And what they did is they looked at the year and they looked at the depth. And what I did is I grabbed this and then I found the numbers. And to make it easier to type, 68 is not the year 68. 68 is the year 1968. Is that clear to everyone? So 1968. And then this 86 would be 1986. Just no reason to write 19 for every number. And then these are the numbers that represent the depth of clarity, how far down they can bring that Secchi dish until it basically disappeared because couldn't see it anymore. Okay. And this is this came from the UC Davis site. By the way, here's a trick question. What do you think R is? Do you think R is positive or do you think R is negative? Remember, R always has the same sign as a slope. What do you think? Thinking of a positive correlation or negative correlation? And R always has the same sign as slope. So if the slope is positive, then you get a positive correlation. If the slope is negative, you get a negative correlation. What do you think? Put it in the chat box. You can kind of see, is this positive or negatively sloped? See if you can type it in. I don't see anyone jumping in, but you should. All right, I'll give up. But okay, it turns out this looks like it has a positive slope, but it doesn't. Because if you look at the meters, this axis, then it goes from 35 to 30, 25, 20, it's upside down. So this actually has a negative slope, even though it kind of feels positive, but it isn't because it's upside down. Figured I should note that before I graph it. I'm going to take these values. I'm going to go to the calculator. Let me go new plot. And then I'm going to paste those values in. And then I'm going to take these values, So the year will be the independent variable, and the depth of clarity will be dependent. Because the idea is we're trying to predict the clarity for a certain year. And I hit plot points. And here it is. You can kind of see, do the points always go down? No. Because, for example, over here, like from 1981 or so to 1984, then depth of clarity went way up. Okay. Then it went down. Then it went up and down and up and down and up and down. But as time went, you can kind of see on average, we can kind of see a downward trend. Do you see that from the scatter plot? Could also see the regression line. And now let's look at all our numbers. So we have R equals negative 0.847. So again, it has a negative slope, so R is negative. R squared is about 0.72. And we'll get to this other stuff a little later. And we can look at the slope. So do you remember that the slope, when we have a line, and here's the equation of the line, y equals 45.6155 minus 0.2465x. So if you remember, the slope of a line is the number in front of x. In this case, it's negative 0.2465. The y-intercept of a line is the number that doesn't have the x involved in it. In that case, it's about 45.6. Any questions on looking at the regression line and be able to determine the slope and y-intercept from the line? Any questions? All right, so now we want to interpret the slope. Do you remember the slope? Hopefully you remember in algebra, is defined as the rise over the run. You remember that? And the rise is a change in y. The run is a change in x. Y is the year. And x was the depth of clarity. So that's going to be important because to interpret slope, we can say that the slope, you can always, even though this isn't a decimal, about negative 0.25, you can write that as negative 0.25 over 1. You can always write as a fraction and divide by 1. You can always do that with numbers. So that 1 means that y goes up by 1. Y is the years. That means if 1 year passes, 1 more year. And then the 0.25, or the negative 0.25, it will be the change in the depth of clarity. So what we can say is that for every year that passes, on average, the lake clarity has tended to go down by 0.25 meters. Notice this is an average. It does not mean it went down every year, because we can see from the graph that doesn't happen. There's a lot of years where clarity went up, down, up, up, down, down, down. So this is not, we know that every year the clarity goes down. You can't say that. It's an average change in clarity, or tendency of an average change in clarity for each year. Any questions on the slope? Okay, the y-intercept. The y-intercept means what is the value of x when y is 0? And what we found is that's about 45.6. But here's an issue. If you look at the data, the lowest data point was 68 for the x value. Nowhere near 0. There's no data points anywhere close to zero whatsoever. If there's no data points anywhere whatsoever close to zero, then it's not, the y-intercept is not very useful because you can't really use the regression line to predict very far away from the data. So we can say that x equals 0 has no relevance because it's kind of far from the data values. So the y-intercept has no relevance. Okay, other times the y-intercept will have no relevance is if it doesn't mean anything to say 0. So for example, let's say you looked at a regression line for how maybe how old somebody is and how fast they drive. Okay, what's the problem with the y-intercept? Any thoughts? If the x variable is how old you are, the y variable is how fast you drive on average. What's the problem with the y-intercept? Should be pretty obvious. Give you a second to type it in. Don't see y'all jumping in, but see, the y-intercept means x is 0. Remember, x is your age. So if somebody is 0 years old, how fast do they drive? That's a silly question, right? People who are just born don't drive. Doesn't even make any sense. Is that clear? So that would be another example where the y-intercept is completely useless. So sometimes it's useless. Sometimes it's useful. Okay. So for the cigarette example, it'd be very useful because then you can predict how long someone's going to live if they don't smoke cigarettes, if they smoke 0 cigarettes a day. Does that make sense? So that would be an example where the y-intercept is useful. But this example, the one we just did, and the age and driving thing there's no relevance. So it depends on the situation. Okay. You can kind of say the best prediction for lake clarity in the year 1900 is 45.6 meters, but it's too far from the data to really make a good prediction. Okay. So now the next thing we can do is say, well, what's the best prediction for the lake clarity this year? And that's the year 2024. By the way, the year 2024 is 124 years after 1900, right? So what we can do is we can take this regression line, which is y equals 45.6155 minus 0.2465x. And we can plug in 124 for x. And that's what I did here. I took 45.6155 plus a negative 0.2465 times 124. And I put that in a calculator, and I got 15. Okay. By the way, I know you're not in Lake Tahoe, but if we look over here, 15 is way up here, okay? Which means that if this year, the year 2024, truly had a lake clarity of 15, our lake would be cloudy and gross and ugly and terrible. Does that make sense? So let me tell you the story, the real story. So again, this was President Clinton. And by the way, President Clinton wasn't the only person there. There were some senators and congresspeople. It was a big meeting in Tahoe about environment. And the UC Davis people came and showed them the data and showed them, the statistics. And basically, I mean, they didn't talk about 2024 probably because I don't know what year they predicted, but if they predicted 2024, they'd say, hey, we only got 15 meters of clarity in the year 2024, and that'll be a complete disaster. So the good news is, again, our president, okay, and the Congress people that were there understood statistics well enough to say, yeah, we don't want that to happen. So what they did is they actually passed a bill that did a big funding for dealing with all of the environmental problems that were happening in Lake Tahoe. And I mean, it was millions and millions and millions of dollars, like maybe even 100 million. It's a huge amount of money. Do you think it worked? What do you think? Okay. It did work. I'm kind of going up ahead, but here's our newest data. And notice if you go from when they passed the law, which is around here, and if you look at the scatter plot post the year 2000, all of a sudden, the clarity stopped getting worse. Do you see that? I'm not saying there weren't bad years, but there were bad years and good years and bad years and good years. But the trend of getting worse and worse went away. And the correlation from the year 2000 to now is actually pretty close to zero. Any questions on that? Okay, so like I said, this is very important to Lake Tahoe. All right. Another thing that we want to do is say, well, maybe we don't have enough data values. Maybe we don't really know if there's a non-zero correlation. So what we can do is we can do a hypothesis test. And the way the hypothesis test will work is it's going to be a hypothesis test for correlation. H naught will be there's no correlation at all, which means the correlation is zero. Remember, the letter we use for the population correlation is rho. I know it looks like a P, but I don't know. That's just the way the Greeks were then. They made it look like a P. Or probably our P looks like their rho because they were before us. So that's the letter that they use. It's kind of a slightly curvy P, I guess, or something. And then equals zero. If you want, for example, if you're doing an exam or the discussion board, you can write, the way you spell rho, by the way, is, if you don't have the Greek letter, is R-H-O. And I always like to remember it is row you boat. But it's R-H-O, not R-O-W. So it's rho equals zero. And H1 is that there is a correlation, so rho is not equal to zero. And that will be the hypothesis. And by the way, for our class, that's going to be the hypotheses for the exams, for the discussion posts, and so for the major things, it'll always be our rho equals zero and rho not equal zero. Okay, any questions on that? For more advanced statistics, sometimes you'll have a less than or greater than, but we're not going to do that. Okay, so I chose not equal zero, and it gave me a test statistic, but it happens to be a student's t-test. Same as like one of the first tests we learned. And it has a student's t-distribution. Again, the math is too hard for me to really explain during the webinar or to any of you if you haven't had like advanced math. So just trust me. The p-value, by the way, is the p-value about 9.67? Is approximately 9.67 to 2 decimals? What do you think? Okay, the answer is no. The p-value can never be bigger than 1. P cannot be bigger than 1. P is a probability. Probability can never be bigger than 1. What am I missing? What am I missing? It's a really important thing, and it's something a lot of people make mistakes on. So I want to really emphasize it. Don't see y'all jumping in. The very end, E negative 10. Do you see that? That means we need to move the decimal place 10 places to the right. And it'll be 0.0000000000967, which is almost 0. So there's our p-value. That's really tiny. So we could say there is very strong, statistically significant evidence to support the claim that there is a correlation between year and lake clarity. Any questions? Any questions on the conclusion to the hypothesis test? Any questions? Okay, if not, let's continue on. And this is a biggie. And this is that when you're writing interpretations, avoid the word cause or causes, because correlation and causation are not the same things. And something that I've noticed a lot of people really haven't thought about, but if you look at the word because, most of that word is the word cause. So avoid the word because has the word cause in it. Also avoid the phrase if da 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 da, then it will. Okay, that's also a cause word, cause sentence. So those are things to avoid. Any questions on that? Instead, you're going to use like words like predicted to be, tends to be, on average has a likelihood of. Those are better kind of ways of wording it than cause, because, or if then. Any questions on that idea? Okay, so for example, I start my morning just about every morning watching a lecture. I was watching a psychology course at Yale, and they were talking about, they did a study, and they looked at how many times a child has been hit by their parent and how much violence they commit when they're adults. Does that make sense? Okay. Do you think there was a correlation between that? Between the number of times parents hit their children and the amount of violence that child ends up committing when they're an adult? What do you think? Do you think there's a correlation? I don't see y'all jumping in. Okay, there's definitely a correlation. I don't remember the exact number, but it was a strong correlation. There was a correlation between that. Does that mean that if you hit your child, that's going to make them become violent when they're an adult? Okay, if there's a correlation of say 0.98, can you say that you hit your child a lot, they're going to be violent when they're an adult because you're making it happen? I don't see jumping in. The answer is you cannot make that conclusion based just on the data. Okay, that's not enough. Okay, it might be that parents who hit their child a lot are hitting their child because they tend to be the ones that are genetically violent. It may not have anything to do with them hitting the child. It might be that it's genetics. Who knows? Okay, you need to actually, see if you can do more to come up with some kind of reasoning. But regression analysis does not give reasoning for causation. Does that make sense? Another one is, let's look at age versus number of gray hairs. Okay. Do you think there's a correlation between how old somebody is and how much gray hair they have? Or let's go the other way. Gray hair versus age. Do you think there's a correlation between the amount of gray hair you have or a person has and how old they are? What do you think? Do you think older people tend to have more gray hair than young people? Should be obvious. Yeah, definitely a correlation, right? Does that mean that if I go and dye my hair gray, then I'm suddenly going to age 10 years? Not at all. Okay, there is no causation to make age happen because you've turned your hair gray. Does that make sense? So that's an example where clearly there's no causation. There may be causation the other way, but but this whole regression analysis does not tell you causation, period. Any questions on that idea? Okay, let me give you one more example that is kind of a fun little example. Let's look at years of successful education after 10th grade and salary in thousands of dollars, okay, when you're 30 years old. And here's data. We have the 6246912 That is how many years of successful education you had after 12th grade. Okay. By the way, any guess how much I had? Any guess? The hint is I'm not one of those numbers, actually. Okay, let's see, jumping in. I had 11 years after 10th grade. Okay. And salary. So I'm going to put this in the calculator. Again, you always want to go to new plot. I'm going to paste our independent variable. I'm going to paste the dependent variable. And hit plot points. Does it look like a correlation? What do you think by looking at it? Okay, I can definitely see a correlation. I can envision this line even if it wasn't drawn. Maybe not perfectly, but it definitely, as number of years of college, number of years of education goes up, income has tended to go up too. Okay. So R was about 0.91. So to interpret R, we can say there's a strong linear correlation between the number of years of successful education after 10th grade and the salary at 30 years old. Okay. And you can even say it's a strong positive because it's positive. 0.9 is pretty close to 1. And that makes it strong. Often if it's over 0.9, then you call it strong. Any questions so far? Okay, R squared was about 0.82 or 82%. So we could say there's a large variation in salaries at 30 years old. If you look at all the people who are 30 years old, some make a lot of money, some make not much money. But if we look at 30-year-olds who all had close to the same number of years of successful education after the 10th grade, then that variation on average tends to be decreased by 82%. Any questions on that? Any questions on the wording? Okay, it's very important you understand this. These are hard to say, hard to write. You'll notice there's a lot of writing. There's no way to make an interpretation with just a couple words. It's going to be a lot of writing. So get used to it. And if you look at some of the ones I've done and you practice, then hopefully you can get good at it too. Notice the equation of the regression line is right here. Y equals about 27.3 plus a negative 27.3 plus 16.4. Okay. So if we want to use the line for x equals 6, interpret it using a complete sentence. So if someone has 6 years of education, which is typically a 4-year college degree after 10th grade, right? It's 6 years of education. Then how do we interpret it? Well, we just plug it in. So I take our value and I use the whole line. And I did negative 27.3391 plus 16.4084 times 6. And what I got was about 71. Okay. So our best prediction for someone with 6 years of successful education after 10th grade is that they will earn a salary of $71,000. Notice it's just a prediction. We can't say that's what they will do. It's just a prediction. That's all we can say. Any questions on that? Okay. I think I wrote this a couple years ago, pre-inflation. Maybe I need to change the numbers so that next time I do this, it'll be a little more reasonable. Okay, the slope was, notice, about 16 or so, 16.4. So for every additional year of education after 10th grade, on average, the salary tends to go up by $16,400. Any questions on that? Because remember, this is in thousands of dollars. So 16.4 is $16,400. Notice that we're talking about an average. We're talking about a tendency. Okay, we cannot say that if somebody goes to college one more year, their salary by age 30 will be higher by 16,400. You can't do that. All you can do is talk about it as a prediction and a tendency. Any questions on that? Okay, the y-intercept is about 27.3. Well, that doesn't have any meaning because that's the y value. And that would mean that your salary at 30 years old would be negative $27,000. And that's silly. Nobody works a job and has a salary of negative $27,000. So in this case, you would just say that there's no relevance to the y-intercept. Any questions on that? Okay. Can you think of an example when there would be a relevance? Like if this equation were different, what would it have to be to have relevance for a y-intercept? Any thoughts? Let's say this was a positive 27.3. Then it would make sense because then you would say that your best prediction for someone who didn't go to school after 10th grade at all, had no successful education after 10th grade, their salary, our best prediction for a salary for someone who didn't go to school after 10th grade would be $27,000. Okay, had this negative not been there, then it would actually have relevance. But in this case, it doesn't because no one has negative salary. Any questions on this idea? Any questions? Okay, what I want to do now is give you the secret word, which is average, because that's come up a lot. Because if you're looking at your slope, for example, then that's on average, it tends to go up or down by that after one change in the x value. So average comes up a lot in this chapter. So average is the secret word. So hopefully you all see that, A-V-E-R-A-G-E. And that's about it. I want to mention how important regression analysis is in the real world. I do want to mention that we do linear regression analysis for two variables. Okay. If you go on and take a more advanced class in statistics, then a couple things happen. One is you can learn about regression analysis from multiple variables. You might have 100 variables. Do you know the number one application of that right now? Where you might have thousands of variables possibly, and then you can do regression analysis. It's a biggie in the news. That's a hint. Any thoughts? I don't see you jumping in. Artificial intelligence. So if you ever want to go into like the coding of artificial intelligence, it's all about multilinear regression analysis. So again, too advanced for our class, but that's a biggie. You could also do nonlinear regression analysis, like exponential correlation. So instead of the best fitting line, you can do the best fitting exponential curve. We don't do that in this class because that would be more advanced statistics, but I want to give you a heads up that it does happen in the real world, but we can only do so much. We just do linear regression analysis. So again, if you decide to go on and do a whole lot more education, then you may learn about it if you take more advanced stats classes. So I think I'm going to call it. It's not one of the super long ones. Usually at the end, we have a little bit shorter webinars, but I will definitely am always available to take any questions after a webinar is over. I am going to stop the recording.